everyone, how are you? I hope you are all doing well. Welcome to my lesson. My pupils, we studied in the previous lesson about energy and types of energy, example types of energy, kinetic energy, thermal energy, but now I want to study about listen, temperature and thermal energy. Please open your book, page 167. Temperature. Question. What is the temperature? Temperature is a measure of the average energy of motion of the particles in matter. This is definition of the temperature. Please underline on your book. Is a measure of the average energy of motion of the particles in matter. Most people think that temperature is a measure of heat, but actually temperature is a measure of the average energy of motion of the particles in matter. Note about temperature at 0 Celsius degree, the particles in the air move more slowly than they do at 27 Celsius degree. Means, example, the particles cold air very slowly than the particles hot air, but the particles hot air very fast than the particles cold air. Question. What does temperature measure? Answer this question. Measure of the average energy of motion of the particles in matter. Please write down on your book than on your copybook. Temperature and thermal energy. Temperature and thermal energy. Question. What is the difference between temperature and thermal energy? Answer this question is temperature measure the average amount of motion of the particles in matter. But thermal energy is the total energy of motion of the particles in matter. Temperature measure the average amount of the motion of the particles in matter, but thermal energy is the total energy of motion of the particles in matter. If has two pieces of matter can be at the same temperature but not have the same amount of thermal energy. Thermal energy and heat and temperature. Another definition, a measure of the average kinetic energy of the individual particles of a substance. Thermal energy, total energy of all of the particles. But temperature and thermal energy, please underline on your book and write down on your copybook. Please look at this video about temperature and thermal energy.
Which has more thermal energy, an iceberg or a cup of hot coffee? What would your answer be? In many cases, the first answer that comes to mind when asked this Which has more thermal energy, an iceberg or a cup of hot coffee? What would your answer be? In many cases, the first answer that comes to mind when asked this question is that the cup of coffee is obviously going to have more thermal energy than a massive iceberg. Are we talking about thermal energy or temperature? How do we define thermal energy versus temperature? Let's find out. In the English language, the common terms thermal energy, heat, and temperature are often used interchangeably. Although they are closely related terms, they each have different meanings and are measured in different units. What are those differences? Thermal energy is the total amount of kinetic energy of the molecules in a system or an area. Being the total amount of energy in the system or area, thermal energy is impacted by size and mass. The base unit for thermal energy is the joule. Temperature, on the other hand, is measured in degrees Fahrenheit or degrees Celsius. Temperature is the average kinetic energy of a substance or a system. Since it is the average kinetic energy, it is not impacted by size and mass. Does this info change your answer? Let's look at the subtle differences between thermal energy and temperature. Let's start by comparing 1 cup of coffee to 2 cups of coffee. What doubled, temperature or thermal energy? Remember, temperature measures the average kinetic energy. 2 cups of coffee will not have double the temperature of 1 cup of coffee, but 2 cups will have double the thermal energy than 1 cup because the mass or size has doubled. Now what about the 1 cup of coffee versus the iceberg? Remember that all substances above absolute zero, that is 0 degrees Kelvin, have molecular energy. Let's assume the iceberg in this example is at the freezing point of water, 0 degrees Celsius, which equals approximately 270 degrees Kelvin or 270 degrees above absolute zero. The coffee is likely to be in and around 75 degrees Celsius, which is 350 degrees Kelvin. While there may not be a huge temperature difference between the two in direct comparison of temperature, the iceberg is several thousand times larger than the cup of coffee. Even though the iceberg is at a lower temperature than the coffee, it contains more thermal energy because it is not at absolute zero, and its mass is much greater than the cup of coffee. Therefore, the answer to the question, which has more thermal energy, an iceberg or a cup of hot coffee, is the iceberg due to its mass. Now, let's consider this situation. If we pour the cup of hot coffee onto the iceberg, does the coffee warm up its area of contact with the iceberg, or does the iceberg cool off the hot coffee? To answer this question, we need to understand the term heat energy. Heat energy is the measurement of energy in transit between a system or area with higher kinetic energy and one of lower kinetic energy. As a unit of energy, the base unit for heat is the joule. Heat energy always moves from the system with the higher kinetic energy to the one with the lower kinetic energy. In the case of the coffee that is poured onto the iceberg, the molecules in the coffee are moving faster due to their temperature. As these faster molecules bombard the slower-moving molecules in the iceberg, their energy will transfer until a point of equilibrium is reached, and the temperatures of the iceberg and the coffee balance out at the same reading. In this example, the sheer mass of the iceberg will not be warmed by the energy transfer from a single cup of coffee due to their extreme differences in area and mass. But if I was to pour the coffee over ice cubes, the same transfer of energy would occur with the faster molecules of the coffee transferring their energy to the slower-moving molecules in the ice cubes. As the molecules in the ice cubes speed up with their newfound energy, the molecules in the coffee will slow down as the energy is transferred to the ice cubes. At some point, the speeding molecules of the ice and the slowing molecules of the coffee will reach equilibrium, and the transfer of energy will stop. In addition to the influence of differences in temperature, heat transfer from one object to another is impacted by the chemical and physical properties of the substances involved. In order to better demonstrate this concept, consider a block of solid aluminum, for example, placed next to a book of equal size at room temperature, 21 degrees Celsius, 72 degrees Fahrenheit. As heat transfer occurs between the air in the room and these two substances, they will eventually all reach the same temperature. This can be verified by using an IR thermometer to confirm that all substances are the same temperature. Imagine holding the paperback book in one substances, they will eventually all reach the same temperature. This can be verified by using an IR thermometer to confirm that all substances are the same temperature. Imagine holding the paperback book in one hand and the aluminum block in the other hand. Which one is cooler? Initially, you would most likely believe that the aluminum block is cooler than the paperback book, as it feels colder to touch. However, both of these materials are the same temperature, as verified by the thermometer. Then, what is causing the aluminum to feel cooler than the paperback book? It is the conductive properties of the two items. The aluminum is a better conductor than the paperback book. Therefore, it will transfer heat energy away from your skin faster. Remember, heat energy moves from the warmer of the two objects to the cooler. In both of these cases, your hand is the warmer object in comparison to the aluminum block and the paperback book. The thermal energy will move from your bare hand to the object. The rate that this occurs is faster in the aluminum block than the paperback book. This process produces the sensation that the aluminum block is actually at a lower temperature than the book, which is not the case. For the layperson, English jargon and the use of it in common speech will continue to impact our level of understanding when it comes to physics and chemistry. Temperature, thermal energy, and heat energy have very specific meanings. Take the time to understand these fundamental terms so that larger concepts are not lost in the translation.
My students, this lesson, please underline on your book and write down on your copybook. I wish it was a useful lesson. See you next lesson. Goodbye.